Hello, everyone. Welcome to this month's iTrain. Today we'll be talking about the basics of VLBI, so a very basic introduction to the science and how you propose for data if you were interested in VLBI. This stands as a part one in this small little series. Part two will give more of a, okay, so now you've been introduced, you proposed, you've got your data. What can you do with your data in terms of reduction and analysis? So today we'll be presented by Kazi, Violetta, Katrina, and Stephanie here. And before we kind of go ahead with the presentation, I'd just like to mention that we do have a Q&A. So in your Zoom, you'll see a Q&A button. If you have any questions as we go along, please do write them in that Q&A. We'll either answer them as we go through the presentation, if anything needs clarifying. Otherwise, we'll answer those written questions at the end of the presentation. So with that, I'd like to hand over to our speakers, and I think Kazi to start.
Yes, hello everybody, thank you for being here. So as Ashley just said, this iTrain on millimeter VLBI with ALMA will discuss mainly the various science cases that you can do with this observing mode. We will discuss the proposal opportunities that are upcoming right now. We will help you with planning an ALMA VLBI proposal and end with an example in the ALMA observing tool for when you are preparing and you want to submit your ALMA proposal. So the second part, which we will do probably in a few months, is we'll start from the point where your proposal has been approved and the data has been observed. And we will discuss how the data is correlated, when you get access to your data, how can you calibrate it, and what parts of your data will end up in the ALMA Science Archive. So to start, millimeter VLBI with ALMA. ALMA can do or participate to millimeter VLBI networks at four ALMA bands. So bands 1 and 3, that is 7 and 3 millimeter. ALMA works together with the Global Millimeter VLBI Array, which you see on your left. And in band 6 and 7, which is at 1.3 and 0.9 millimeter, ALMA works together with the Event Horizon Telescope. Now, you probably know that VLBI stands for Very Long Baseline Interferometry, and very long baselines indeed, as you can see from these two world maps. So the baselines are really on the order of the Earth diameter, so 10,000 kilometers or more, the longest baselines. This is about an order of 3 magnitude more than the longest baselines with ALMA only, which are 16 kilometers. So this means an order of 3 increase in the angular resolution of your data, meaning that all the science cases for millimeter VLBI are driven by the need for very high spatial resolution, as you will see next. So ALMA joined the millimeter VLBI networks only recently, and I believe in 2017 were the first data to be taken, including phased ALMA. Why was that so important? Because ALMA, when ALMA observes in millimeter VLBI, it observes as a phased array using 37 12-meter dishes to work together as if a 73-meter diameter single dish antenna. So that makes it the largest millimeter antenna on Earth and the most sensitive one. That's why the inclusion of ALMA was crucial. In addition to its sensitivity that it brings, it's also very important for the UV coverage, because it's one of the few antennas that we have in the Southern Hemisphere. So for both of these two things, it was essential for the Event Horizon Telescope that phased ALMA participated in their observations of 2017 to detect the ring around the supermassive black hole in M87, as you see in this image. So one of the main science drivers for millimeter VLBI were indeed to make the first images of a supermassive black hole, which is what the EHT collaboration published for M87 and for the supermassive black hole in our galaxy Sagittarius A star. Here it was essential to be able to resolve the lensed plasma around the supermassive black hole at event horizon scales. Right? And only using millimeter VLBI, this was possible. And this is also the only 2 supermassive black holes for which this is possible. This these images gave very important information for the inner parts of the accretion disk. And also because all millimeter VLBI observations are in fact polarization observations, also magnetic fields could be measured, and they are already published from M87 stars. And this magnetic field information is very important because it provides strong constraints on accretion disk physics. Another field for which these images were very important is gravitational physics. So given the mass of the supermassive black hole and the distance to this object, general relativity could exactly predict what the diameter of this ring should be. And it was beautiful to see that both of these observations confirmed general relativity. Now, there are, of course, many other science cases that we can do with millimeter VLBI, with continuum observations of millimeter VLBI. For example, active galactic nuclei launch, or some of them launch jets in which angular momentum is carried away from the central object. Now we can see these very large jet structures on tens of kiloparsec scale. So on the left, you see a composite image of Centaurus A. Right, and you see there is this giant jet going out of the central object. When looking at the central object in centimeter VLBI, so this is the central image which was published by the Tanami collaboration, you see that this jet is highly collimated. And then we're looking at it even at a higher resolution, and now with the Event Horizon Telescope, including ALMA, so that's a zoom of more than 1 million times with respect to the composite image, you can really look at the jet launching region and also see there that the still highly collimated structure, now also edge brightened, and interestingly, having as the same orientation as the large-scale jet emission. So millimeter VLBI is very important in the studies of jet structures and jet launching. Also in the next example, this is an interesting source in which jet structure is very interesting. So we have here Blazar OJ287, and it's a binary black hole candidate. You can see in both images are taken with a GMVA of the central part of the jet, and you see that it has this wiggly structure. On the left side, we see GMVA at 3 millimeter without ALMA, and on the right side, we see GMVA observing is still at 3 millimeter, but now with ALMA. And you can appreciate immediately the difference that ALMA brings to millimeter VLBI in sensitivity, but also, of course, in angular resolution. As you see in the bottom right, you see the UV coverage, and the red dots are really the baselines to ALMA, giving an exquisite, showing an exquisite detail now of the structure also in north-south direction. And now, so far, all the examples that I've shown are from continuum millimeter VLBI. But ALMA also does, since recently, spectral line millimeter VLBI, of which the most important spectral lines to study here are maser lines. Why masers? Because masers are very bright and very compact sources of emission, and we need this kind of structures if we want to go using VLBI. In addition to having high spatial resolution, spectral line gives us the advantage of providing also velocity structures. This opens the door to kinematic structures, as for example, in this case, to study the kinematics of the inner parsec of the accretion disk of galaxy NGC 1068 using the high sensitivity array and using, in this case, 22 gigahertz or 1.3 centimeter water masers. For a very small number of targets, we can also study, we can also do VLBI with molecular absorption lines. Why do I say very small? Because in this case, we have to observe the molecular absorption lines against a very bright and compact continuum source. So a bright AGN core is a very good candidate for this. And in this study, which is not a VLBI study, but it's ALMA band 6, ALMA only, an interferometric study, you can see how towards the AGN, you can really see molecular absorption lines in the spectrum. While when you look aside of the AGN, you can see emission. So with VLBI, you would not see the emission part, but you would be able to see molecular absorption lines at a very high angular resolution, right? And this is very important to study the inner part of the disk, the molecular cloud dynamics there, and to understand better how AGN accretion and feedback work. Now, also in our galaxy, we have a number of topics, a number of science cases which are very interesting for millimeter VLBI using masers. In particular, I would say masers around forming stars are very interesting. So star formation is a very important topic, and there is still a lot of unknowns in how exactly does the material from the disk get accreted on the young stellar object, and how does it work together with the outflow and the winds that bring angular momentum again away. So to have accurate comparisons of the kinematics, to accurate comparisons to models, we need to have very high angular resolution information, both the spatial information on the gas and the kinematic information. And that's where maser VLBI can really be a very important contribution. In this example that I show here, these are global VLBI observations in the centimeter, again, 22 gigahertz water masers. And this is the first observation of a magnetohydrodynamic disk wind, which is important for carrying away the angular momentum. So in this case, angular scales, spatial scales of 1 to 100 astronomical units have been reached. And when using millimeter VLBI, you would be able to go below AU scales. Masers around evolved stars are also a very interesting scientific field. So we know that evolved stars have a very strong mass loss. They have mass which is concentrated in shells as it is transferred out into the ISM. Various maser transitions trace back different parts of these shells, as you can see in this image, where 4 transitions of SIO masers trace a very nicely and spherically symmetric shell around the star, while the water masers are really scattered all across in a larger area around the field, right? And this can tell you something about the mass transfer. What I forgot to say here is that also here angular resolution is very important, because these shells are something between 4 up to 20 astronomical units in diameter. So all of these require high angular resolution observation. So as you might have noticed, none of the examples from spectral line millimeter VLBI that I showed included ALMA. That I showed one ALMA only, and the others were centimeter or millimeter VLBI networks that do not include ALMA. This is because spectral line VLBI is a new ALMA capability, right? And there is no published results yet. So it's a really exciting field, and you can now really be at the forefront that is pushing this, will be pushing this field. And to get you excited, we put here a number of maser transitions that are available within the ALMA bands for VLBI. Those are bands 1, 3, 6, and 7 of ALMA. And these masers include water masers, in particular, SIO masers, HCN masers, and methanol masers. We do urge you to always check also the compatibility with the other antennas in the arrays for the when you have picked a spectral line, because each of the antennas might have a slightly different receiver and receiver range. Also for this, you can of course always contact your ALMA regional center node to get help on whether your idea can be done with the millimeter VLBI network that you're interested in. So as a summary of science cases, you can give a look to the papers by Fish and Tilanis. And now I hand over to Violette that will talk a bit more about what are the possibilities for these proposals.
Thank you, Kazi. Thank you. Yes, let me share the second part of this talk, my slides on 1 second, because I need to get everything in order here. We're going to talk about how to apply for ALMA VLBI and what you have to do if you're new to this. And the aim of this talk is indeed to invite more people in our ALMA community, people who have not used VLBI before necessarily, who are thought about using VLBI, to be able to participate to ALMA VLBI. One of the main messages, or actually the main message I can give you right now, is if you're new to ALMA VLBI and you're thinking to apply and you have an interesting science case but are unsure, please write to us, send us a message, whether it's via the help desk, as actually preferred, and the help desk will send it to the appropriate person. Or if you already know who the appropriate person is, you can also informally contact us first if it's an easy question. We can help you, and we look forward to helping you. So yes, how do we observe with millimeter VLBI? You see my slides well, the slides show. We tested this before, but
We see them fine, Violette.
perfect. Thank you, Kazi, for confirming. So the millimeter VLBI observing mode has been growing a lot in the last several years. I really like this slide in particular because it shows not only the first set of antennas that were used in the past millimeter VLBI observations, but also new ones that have been added more recently. For example, the Greenland telescope that's still been commissioned, but it's already observing. NOEMA is now added also to the array, and also upcoming antennas that will be joining the various arrays. And it's really a growing field. There's going to be more and more. The UV coverage, already you can see all the baselines, is also getting better with time. And so it's a really exciting time to join the ALMA VLBI. There are 2 main arrays currently. And so which one is right for you? How would you choose which one to observe? Generally, I think it would be helpful as a user to not think about the 2 arrays, but to think about what kind of science you're interested to do and what do you need. What band do you need? What frequency do you need? If you're looking for continuum, if you need band 1, if you want to do SEDs, if you need more resolution, also the frequency will play a role. High frequency bands will give you high resolution as well. If you're more interested in sensitivity, how many antennas, this will play a role. So use the science to lead you about which band you want to use. Then depending on the band, or actually, I'd also want to mention if you're doing lines, also depends which lines you're after, and that will take you to whichever band you want to use. So if you're using band 1 and band 3, these are the ones that are currently available, you will be joining the GMVA observations with ALMA, and if it's band 6 and band 7, you will be joining the EHT. And only those 4, as already mentioned by Kazi as well, only those 4 are available at the moment. However, I say only those 4, but they're actually growing as well because band 1 also was a recent addition, as was Spectraline last year. So if you end up observing with the GMVA, there are 2 deadlines for this. The first one is January 31st. That's in a little bit more than 10 days from now. And you have to resubmit the same proposal at the ALMA deadline. That's on April 25th. If you are observing with ALMA DHT, there's only 1 deadline for you, and that's via the ALMA OT, and that will be on April 25th. Makes it a little bit easier, but both cases is pretty straightforward because it's the same proposal going in. Again, a reminder here that the GMVA deadline is coming up. So if you're interested, please, you should start writing your proposal. And also, if you have questions, again, let us know, or we get you in touch with the GMVA. If you do miss the January 31st deadline, you will have to wait a year to observe again with the GMVA and ALMA. If you only want to observe with the GMVA without ALMA, there is a second deadline in August. Also keep in mind, this is until now is true. It may not always be true, but until now it's true that if you apply for ALMA time with EHT or GMVA, observations are likely to occur in April. during a special campaign. And so you have to think about when your source will be up at night at ALMA in order to also estimate uptimes, UV coverage, and when your source is visible at various sites. So this is something that's good to keep in mind already, as it's already known. There's more information online. Actually, I put a link here. This is very useful. It has a lot of guidelines, and there's also links to the various sites. And this is through the German node in Bonn. This is what the GMVA call for proposal looks like. It's hosted at the Max Planck Institute in Bonn. There's various guidelines. And again, for the 31st proposal, GMVA deadline, we use the NRAO proposal tool. And for ALMA, use the ALMA OT that you all know and love. For the EHT call for proposal, in summary, the 25th of April is your deadline. You only submit using the ALMA OT. More information is going to come out in the call for proposal that's going to be announced in March 2024. There's going to be more information also on what you can observe. And one of the new additions will be that you can, this year in cycle 11, that you can submit for more than one target per science call for VLBI. Last year, the actually really exciting addition was spectral line and band 1. So every year there's more coming. Please check the call for proposal in March. So just a little background here, a little bit of a short history and how it works. How does ALMA participate to VLBI? ALMA is an array itself, and how does it join a different array? The answer is the ALMA phasing project. This was started already early on during ALMA commissioning itself. The ALMA phasing project foresaw that it was going to take advantage of ALMA's extraordinary sensitivity to join the sub-millimeter array to observe the black holes that, as was described historically, as was described by Kazi. This was early on. This already 2011, 2012. Work towards APP was already started in parallel to ALMA commissioning. And the idea is to combine the signal to all antennas. So sum the signal to create to simulate one big single dish antenna. So for 37 antennas of 12 meter, you get a 73 dish equivalent. So you take the square root of the number of antennas times 12 meters. 37 antennas is not the maximum. This is sort of what ALMA proposes, what ALMA promises, but it can be more if the more antennas are available. But more or less 70 meter is what you get. And this is a huge antenna, huge single dish antenna in the sub-millimeter regime. So it really boosts the signal. Also, ALMA is located in a very good place, and the conditions are excellent for sub-millimeter observing. They are the best in the world. Also, it was already mentioned, but I'd like to say a little bit more about sensitivity. ALMA is not only corresponds to a very large dish, but also has very good electronics. And one of the ways to think about this is the noise of the receivers. A proxy for the noise is the system equivalent flux density, SCFD, which depends on your system temperature. So the higher the temperature, the noisier are your receivers. So you want less noisy receivers. That means you want a low number. So for phased ALMA, you have an SCFD of about 94. And you see as you go down other EHT sites, the system temperature goes up. So this, together with the large equivalent dish, makes ALMA very sensitive to very faint signal, which is good for observing and imaging, but it's also good for calibration. And it's also good for correlation. So when all the signals here on the right are correlated, they're all cross-correlated for fringe search to ALMA first, and then they're cross-correlated among each other. So ALMA is very key, and as a full member of the EHT and the GMVA array. For the phasing, it requires, you have to remove in real time phase differences between each pair of antennas to a reference antenna, and then you add them coherently. And this results in a boost in the signal. So this is a screenshot that I took some years ago, which is really exciting to see in real time, where you see here low is the unphased signal. After applying phasing, the signal goes up when you add it. And of course, this actually shows for different basebands and polarizations, that the phasing efficiency is very high typically, and it's one single dish, corresponds to one single dish. In order to do this, however, we also need a phasor. So we need a strong signal on which to apply this correction that we use to determine what the corrections are and apply it. The phasor can be active or passive. What does that mean? An active phasor is when the target itself, say you're observing M87, the target itself is strong enough to act as a phasor to determine those solutions. If the target is not strong enough, say you want to observe really faint target that doesn't have strong continue, then you need to have a passive phasor. That means a second target which will be used to phase your antennas, and then you go back and observe. It's a bit like phase referencing. So active phasor is the target itself, and a passive is your phase calibrator, is a nearby calibrator. This is very important if you're thinking to apply for a millimeter VLBI with ALMA, because, and it's probably one of the most critical points for your success of your observations, because you have to have a strong enough target, either active or nearby, and I'm going to get to nearby in the next slide, to be able to observe, to be able to have ALMA phased up. So you need a bright source. For active phasing, so there are some guidelines. Actually, for more information, please do refer to the technical handbook. It has a lot more details. So how strong your target has to be for active phasing depends on your band. If you go up to band 7, you need a much stronger source. If you go to band 1 or band 3, it will be, less strong. So 350 millijanskis, for example, in band 1. And if you go up to band 7, you need 750 millijanskis. This is also true if you want to observe a line. If you know you're observing an SIO maser, for example, like Kazi was saying, and it's really, really bright, 5 Janskis or 100 Janskis, yeah, you can probably phase on it. However, you have to also be clear about how wide this line is, and that also plays a role. There's a formula to determine whether your line is strong enough for phasing. Again, I refer to the technical handbook, or to contact us if you have doubt. So if you're using active phasing, all you need to know is how strong is your signal to phase up on ALMA. If it's not strong enough, you need to think about as well how nearby is your passive phasor. And that depends again on your band. So for band 1, you can go up to 10 degrees. This is the same as phase referencing, actually. If you go up to higher bands, band 6 and 7, it becomes more critical, and you want to find a passive phasor that's within 3 degrees. Will be phased up, and then you go back. This can be a problem in some cases. So again, please contact us if you have problems finding a passive phasor. You have to also think about suitable targets for millimeter VLBI. So this is something that was covered in the science of Kazi. The common science was that all targets, whether these are masers, compact objects, AGN, are really compact enough at tens of micro arc seconds so that you can detect them on the longest baselines. If you know already that your target will be resolved, you should write that in your proposal, and you should argue why. Even if it's resolved on the longest baselines, you still have enough signal, and the science is interesting enough to use on the mid baselines. So these are considerations that you need to take into account. Other requirements are that the target has to be visible by most of the antennas, at least sometime, and the UV coverage is good enough. So this is a plot created with the EVN observation planner. We're going to have a short demonstration of this in a few slides. This is a really nice tool, and it really helps with planning your VLBI observations. In this case, you can see that for time, this is your time of observing, your sources go up and down, and these are your in this case, EHT target antennas. And you can see when your source is visible at any given time by which telescopes. And this is extremely important for VLBI observing, and it's something the observatory needs to know. Also, consideration is how long your tracks are. The longer you observe, the more these tracks will be filled, and the better is your UV coverage, the better will be your imaging and your data source and your data and your results. So it's a good thing to play with these numbers and to have a look. So you don't just think about time, you actually think about also your UV coverage. There are more special constraints that I'd like to mention so you're aware of them. For example, that all VLBI observations with ALMA are treated as full polarization. That means that all observe for a minimum of 3 hours, but this is really a minimum. Usually for VLBI, you want to observe at least 6 hours to full track. The source is up, so you want to observe the source all the way, covering enough UV coverage, but also you want to make sure you have enough sensitivity. So 3 hours is the minimum, but usually you do at least 1 or 2 tracks. Your UV coverage is sparse, I already mentioned this. It's good to go for longer for good image fidelity. And here I would like to mention spectral line observations. You can choose your spectral line setup pretty much freely at ALMA. You can really put your line wherever you want, and ALMA will be able to tune to it. This might not always be true for all the stations. So if you are, this is the message again, if you are thinking to do spectral line observations, and that will be really great. It's a mode that's just recently been introduced, and we'd like to see more of it in our science, especially these long baselines. There's a lot of discovery space there. However, because it's also new, if you are thinking to do it, I would recommend that you contact us via the help desk, and we help you, with the spectral tunings of the other stations to check that things are possible and they can be tuned. Finally, please think about array-specific information. This depends on your uptime, when your sources are up, but also your signs, what you want to resolve, what is the compactness of your sources, and what you're thinking to do. Okay, so I'm gonna do a little bit, show you a demonstration here. That was on the EVN observation plan that was put together by Kazi, and I'm gonna show how this is really nice tool that's been recently released. This is the link here at the top, and you have either a guided mode or a manual mode. We like the manual mode. And already here, you can see if you go scroll down, you can in principle choose your antennas. You have a lot of options. Again, it's a really nice generic tool. But once you choose the bands, and so here we go, for example, for, wait for it, 230 gigahertz, that's band 6, and you choose your source, M87. Already a lot of all these stations get crossed out and the appropriate stations already get selected. So you can start your observations, and you already know we're going to observe, as I mentioned before, in April 2025. So we're going to go all the way there. And you select a time. There will be nighttime at the station. At the station. And we select 8 hours in this case, 40% of time on source. The rest of the time is for calibration. This is typical. We select a data rate for the stations, which is the maximum number, the highest data rate that we actually observe at. Number of channels, polarization, and integration time. You can use these numbers as defaults once you've seen them. And then we go to our array, which is the EHD. This is band 6 again. Okay, so once this has all been selected, you click on Compute Observations, and you get a really nice summary that you can play with to optimize your observations. So the summary tab is now open, and you can see your frequency setup, your observing time, the resolution that you get, so you can actually check on your target whether you have enough flux density for that particular resolution, and the observing time that will be the sensitivity. And here, this is the plot that I showed you earlier. This is the uptime, and you can see where the sources are for various stations. This is extremely useful for planning and also for the proposal. Again, you get a UV coverage. You can play with longer times, and you can see how UV tracks vary. There's more in this tool that can be done here, but it's really useful and really nice to actually play with, and it's very instructive, especially to people who have not used VLBI before, but also for So more special constraints on calibrators are already mentioned. The calibrators need to be selected, especially for the phasing. But it's good, always good in your proposal to mention more calibrators, especially if you know there are good fringe finders nearby, polarization calibrators. If you're already aware of nearby strong calibrators, please do mention them in your proposal. There is a lot of resources online. I would like to first and foremost mention here ALMA. This has got, shows what it looks like. If you click on that link, it has a lot of information on the polarization of all the calibrators, and it's really the first place to go to search for resources. It's kept up to date by Seiji Kameno, and yes, it's a first stop. There is also more information in the ALMA source catalog and in the SMA calibrator database. And finally, again, in doubt, contact us. I'll put together a text for technical justification. This is a bit on the long side. It doesn't have to be that long, but just to kind of show various examples of various things that can be mentioned. This is a fake technical justification, and it's certainly not a template. So you do not need to fill everything if it's not relevant for you, but it gives you an idea and a feel for the type of information that needs to go into the technical justification of the ALMA OT. I'm not going to go through it. You can watch this again and pause if needed. But it's good to have a feel for what kind of information is needed. There is also more information online on the GMVA website, call for proposal. There is more information if you click here, and you can see also specific things for GMVA. You have to specify, for example, you have to say ALMA, another station in the text field, and whatever default observing modes and data rates are. Also, the Event Horizon Telescope for astronomers, the website is technical justification. There's a lot of very useful information. Just please have a look there and only mention whatever information is relevant for your proposal. You don't have to mention everything. Here's a demonstration on the OT that was put together by Katharina Immer. So I'm going to mute myself and I'm going to play this for you.
You have to unmute, Violette.
For example, we can choose M87.
Sorry, let me start again.
Hello, everyone. In this short video, I'd like to give how a VLBI proposal looks like in the ALMA observing tool. You start with a new proposal and you fill in the usual proposal information as for a regular proposal. Then in the proposal type, you choose VLBI. Now you can start with adding a new science goal. We'll first fill out the field setup, where we have to specify the target that we want to observe. For example, we can choose M87, resolve the source, and then we get the usual coordinate information. As you see, different to regular proposals, you don't have to fill out a lot of expected source properties. The only thing you have to specify for continuum observations is that your source is stronger than 350 millijansky. If this is not the case, you have to click here so that ALMA knows that passive phasing is required for your project. I'll come back to that a bit later in the video. It is now also for cycle 11 possible to have several sources in one science goal as long as they have a distance in rate ascension of less than 3 hours. Now in the spectral setup, you have two choices. You can either go for a single continuum setup or for a spectral line setup. For the single continuum setup, you can choose from the 4 different receiver bands that are VLBI compatible: band 1, band 3, band 6, and band 7. If you choose one of them, then the frequencies are preset for you. If you want to observe at different frequencies, you have to use the spectral line type. And here you can either add a spectral window manually. Say I want to observe at 330 gigahertz. But then for baseband 1, I have to make sure that I use the correlator mode 2-bit plus VLBI. If the other basebands are also to be observed in VLBI mode, then they have to have the same correlator mode. If they are to be observed with ALMA alone, then they can have any kind of correlator mode set up as under the rules for ALMA observations. If you want to start with a VLBI default setup, you can also come here, select band, and then select one of the 4 bands that are possible for observations. But you see now here, the frequencies have been chosen for you, but you can adjust them as you see fit. You have to make sure that the YOLO solutions that you get are, and the observations that you set are compatible for all VLBI antennas. Let's say for now that we want to observe a single continuum observation. We can now go to the control and performance section and fill out the VLBI total time. This is the total time per science goal. Since VLBI observations with ALMA are always full polarization observations, these have to be at least 3 hours long, as has been explained before in the presentation. Now, if we have several clusters, because we're observing several sources in one science goal, we have to make sure that the VLBI total time is at least 3 hours per cluster. So let's set now 6 hours here. This is, of course, given also by the sensitivity you need for your observations. And if you go now to the technical justification, you here have to fill out a lot of information that is important for your VLBI observations. This has also been discussed before in the presentation. Let me just put an example here. So now you have here the different information which you should just justify. There's also the 2 different arrays, EHT and the GMVA, give examples of what has to be filled in here. Now, so this is also already enough for a VLBI continuum observation. So if you now validate this project, there are no problems found. If you instead choose spectral line observations, so you click here and say spectral line, then you also in the control and performance section, you have to say that your observations are time constrained, and you have to specify when these observations are taking place. Because the Doppler corrections have to be calculable for your observations. So you can come here, edit this observations. You can come here and say, for example, I want to observe in April 2025. Let's see here from here to there. And this is adjusted directly, but you can also adjust this yourself. You come here and okay, this looks good. And then also in the technical justification, there is now a new window that opens, but you have to justify your time constraints and say why you want to observe at these times. Another thing that opens up is here in the field setup, where you now have to give the line width of your source. So for example, let's say this is 10 kilometers per second. This is all the information you have to give, and now it should be possible to validate again. Of course, I have to fill out the technical justification. Let's fill something here. And now the project validates without problems again. If it is the case that your source is not strong enough for active phasing, then you can click here this button. You see now that this has changed a little bit because we're doing spectral line observations, and these have slightly different limits than for continuum observations. So if you click this here, then your calibration setup changes and you now have user-defined calibration. So what you have to do now is to specify a calibrator for your phasing. So you have to come here, say fixed calibrator, create a phase, and then a new window opens up that looks like this, where you can choose your phase calibrator. So this should be a sidereal target, and you can say, I want to select this from the source catalog, and then you can choose, you can search for, okay, let's say for, you can search for your calibrator. Let's say we're going for this one. So you can do select calibrator, say okay. And then you have this calibrator selected. You can say okay. And this is now the calibrator that will be used for the passive phasing. In the technical justification, you now have two more boxes that you need to fill. One is for the user-defined calibration, so you have to justify the selection of the different calibrators that you've done. And here you have to justify the calibrator itself that is being used for passive phasing. So again, this needs to be filled with 50 characters, so let's do that. And now the project should validate again. So these are the different options for your VLBI project. And once you're done with all of this, you can go ahead and submit your project. And you're done. Good luck with your proposals.
Okay. Very good. So let's go back to our observation, to our next
Hello, everyone.
Slide. Okay, so now you've wrote a proposal and say your proposal was accepted and you're very, very happy about it. I'll start my video again as well. And what happens next? We'll talk more about this in the future, but just in a nutshell, short summary, if your ALMA VLBI proposal is accepted, it will be passed on to our scheduler in this network, and they will build schedules. They will get in touch with us. They will get in touch with the PIs, and there will be some fine tuning on the actual final schedule. So this will go via the observatory, and you don't have to do anything in practice, at least not proactively. You'll be contacted. But that's for next time. There is documentation and help online. There's a lot of documentation and help online. I already showed you the GMVA HD sites. There's a lot more information than what we have shown here for time. We cannot go into every detail, but there's a lot more information in the technical handbook that's kept up to date, especially in chapter 11 for the coming cycle. And again, there's source catalogs that are very useful. So good luck proposing, and we will have the second iTrain will be advertised on post-processing and VLBI reduction. So please stay tuned for that. And thank you for your time. And I'm gonna now ask the other panelists to come back online, and I give the word back to Ashley, and we'll probably take questions.
Thank you so much. I guess I'd like to join, everybody virtually in thanking you very much for this very nice presentation. So virtual applause. I guess I will stop the recording here. So there's no pressure in answering or asking, I should say, questions in the Q&A session.